Welcome to lecture 13. We'll continue our course through fluid mechanics. Just some quick announcements. So homework 3 is due on Monday, and Felipe has booked E1B11 on Monday from 3 to 5 p.m. to answer any questions for homework 3, and we'll also again announce on Monday. I will naturally have office hours today and again on Monday, so you should have sufficient information. And as I will explain today, we have uploaded another video. So for each problem of homework 3, problem 2, 3, and 4, you'll have one video each to support for each problem. So it will hopefully help. Okay. So let's carry on with our discussion from last time. So quick reminder: we have been discussing about stress tensors, then stress vector, which was Sn of n dot sigma. And then force is actually stress vector integrated over the entire surface. So if I'm asking you to calculate force, which is what we will do today a couple of times, it's actually integrating force, integrating stress vector over the area. Then we said, okay, there is stress tensor, but we'll break it down into two parts. One part is the pressure part, which is pressure is a scalar, and we'll multiply it with an identity matrix. So it's only in the normal direction. So pressure only acts in the normal direction. And then we have a shear stress vector, which comes because of flow. So this part tau comes from flow. So this part is related to flow. Okay. So this part essentially is related to flow. And when we derived an equation, which I'm not going to detail, Cauchy momentum equation. And then we said we'll actually substitute tau as mu outer product of V plus mu outer product of V times transpose. And this is assuming constant viscosity. If we substitute this in the Cauchy momentum equation, we get to the Navier-Stokes equation, and combined with continuity, this is our governing set of equations. And remember that this is only true for constant rho, constant mu. So if your viscosity is changing or density is changing, please do not use these equations. Okay. Especially if somebody is working in polymers or some non-Newtonian fluid like biological fluids are often non-Newtonian, you will not be able to use this. Okay, so just remember that. Yes.
Where does the transpose go?
So if you basically put it back, it just it becomes del square V. So it's just vector identities. So yeah. Any other questions? All right. So one thing I did forget to mention last time is that this compact form of equation is not something you'll necessarily use every time, because these are vector equations. So if you want to basically look through the book has a few tables. So table 6, 7, 6, 8, and these are basically scalar form of those equations. So you have 3 equations each time. It's a vector equation, so you can convert it into scalar equation each time. And essentially you get to these equations. Note that basically if you will be using cylindrical coordinates, you will be, some of the equation terms may not look as familiar because you will be changing coordinates. So the equations become more complicated. Okay? So just remember that. We have often seen when we give problems to students, sometimes students just don't look at the table and they just start to guess like an equation. Just always come back to look at the equations. They really are important. And similarly for spherical coordinates, and spherical coordinates even more complicated than cylindrical. So we'll primarily focus on Cartesian, but we'll have some problems to give you exposure of what happens in cylindrical and spherical coordinates. Okay, so you can always look this up in the book. All right, so just remember that this is table 6, 7, 6, 8, and 6, 9. So this is table 6, 7, 6, 8, 6, 9. These are handy tables to keep in mind during homeworks and exams. We have to look in the book. All right. So this is our governing equation. So stress tensor, stress vector, force, then shear stress and pressure term, and then we use the Newton's relationship for shear stress, and then we get to the Navier-Stokes equation, which are set of 4, basically combined with continuity. There are 4 equations, 4 variables, and the variables being Vx, Vy, Vz in the Cartesian coordinates and pressure. Okay, so these are the 4 variables we want to solve for. All right. Now the next part we discussed was boundary conditions. And the boundary conditions, I will not look at the full detailed equation. I'll just see the kind of practical scenarios we will discuss. So that's fluid solid interface. We will use a no slip condition. So remember, this is no slip. This is no penetration condition, which is comes out of mass balance. Okay. Then if it's a parallelly moving solid, will be given a velocity. So we'll just equate the tangential velocity to that. Or if it's a porous solid, you can have a velocity v naught in the normal direction. Then if you have a fluid interface, so this is the part which is called hydrostatics. So if I have hydrostatics, then I get rid of all the equations except P1 minus P2 plus 2H gamma is equal to 0, where H was, remember this was curvature, and gamma was surface tension. Okay. If we have a liquid air interface, then we typically assume viscosity of the air is 0 and surface tension is constant, and liquid cannot permeate through air, in which case we will say normal velocity is 0, but instead of no slip, we'll apply no shear stress condition. Okay, so remember that no slip is not valid. Is not valid for fluid air and liquid air interface. Okay, no slip is not valid in the sense like in traditional way. So no slip will be valid if I was also solving for if I was also solving for the air velocity, but right now we are not doing that. So you don't apply the no slip condition like you do for a solid surface. Okay, just remember that, because we don't solve for the fluid velocity and fluid might be moving on the other side. So we don't apply it, we just apply the shear stress in the parallel direction. Okay, any questions? Yes, no.
On the boundary conditions, the left is that dt equals
U, yeah. So some velocity U, given velocity, capital U will give, like, it could be some function, or it could just be some value that will be given to you. Okay. And if it's a liquid interface, you will have all four boundary conditions, which I'm not describing because it takes a few minutes to describe it, but you will have to use all four boundary conditions. So if some of you are using emulsions, and if you're interested in working on some understanding what happens in a liquid interface, you actually do have to use all four interfacial conditions to understand the flow. Okay, so there's a full literature of what happens when there's a drop within a liquid, but we are not covering that. It is just an extension of what we do here. Okay, so it's not too difficult, but it just takes more time. We will not cover that in class. Any questions on boundary conditions or governing equations? Okay. So whenever you see a fluid problem, remember Navier-Stokes equation is true for constant and constant mu. If density is constant, viscosity is constant, you can use them, and then you can figure out which part of the boundary conditions you are at, and then apply those boundary conditions. Okay. All right. So we started focusing on one of the problems, and I will just to recap. We were focusing on the problem of hydrostatics, where velocity is simply 0. We were given a solid cube which was submerged halfway into water, and we said we had x, y, and z directions. We said the density of this is rho s, and the density below is rho. The pressure outside is P naught at the air, and we basically ignored the density or any changes in air. Air, the pressure is just constant P naught, and and what we had basically shown was using buoyancy force and gravity force. We can say it's 0, and the buoyancy force is given by minus rho v submerged. So let's make it capital V. V submerged times gravity vector. Okay, so it acts opposite to the gravity force, and gravity was acting here in minus EZ direction. So buoyancy force acts in positive EZ direction. Rho v submerged times g, where rho is the density of the liquid. So it's the weight of the liquid displaced by the solid, is the buoyancy force or Archimedes principle. And if you balance with gravity force, we got that rho s is equal to rho by 2. Okay, so that is what we got. So the next step we started thinking about was what is the origin of buoyancy force? What is the origin of buoyancy force? And we basically kind of discussed that we will show that this is actually equal to the pressure force, net pressure or hydrostatic force coming from the pressure. Okay, so we want to show that. And when we started doing it, we said, okay, well, we'll start with the governing equation. And the governing equations are rho del V by del T plus V dot del V minus grad P plus mu del square V plus rho G. This goes away, this goes away, this goes away because viscosity is zero. Sorry, velocity is zero. And essentially we found that grad P is equal to rho G is equal to minus rho G EZ, because the G vector, remember, is in the negative EZ direction. And from this, we basically got del P by del X is equal to 0, del P by del Y is equal to 0, and del P by del Z is equal to minus rho G. Okay. So I'm just repeating my steps just so that you can remember where this came from. And from here, essentially, we could say P is equal to minus rho GZ plus C. Okay. So where C is not a function of X and Y, because C is a constant, because pressure cannot vary in X and Y. Okay. This is very important. I want to really emphasize this part. And you may have done some of these questions in your undergrad, hydrostatics. I want to emphasize how this comes from mathematics. The reason that is because we will go towards much more complicated interfaces, not necessarily just a solid block like this. So remember, pressure is not a function of X and Y. Okay? It only changes in the direction of gravity. And in the supplementary video, you will see we'll have a cylindrical geometry, where the gravity is happening in the combination of R and theta direction. So it becomes a little bit more complicated. And so you'll see in the system how to think about gravity and pressure in different directions. So take a look at the video, it will help you. But just remember that this comes from that. Some students just directly write this equation for any system. It's only true for the coordinate system you chose. All right. So this was the governing equation. The second question was about the boundary condition. And we very quickly discussed this and stopped here. Boundary condition was, which is the boundary condition we should apply. Okay. And always the question now is, looking at the geometry, there are many interfaces, right? There's a solid air interface, there's a solid liquid interface, there's a liquid air interface. And we said what we want to really find is the constant for pressure. Okay, we want to find the constant for pressure. And if I go to my boundary conditions here, I can clearly see the pressure only comes in the equation when I have a fluid-fluid interface, right? Fluid-fluid. In this case, the fluid-fluid interface has to be the liquid air interface. So that was the rationale of using this boundary condition. So that's why we used the fluid-fluid interface to calculate pressure. Fluid-fluid interface. And that is at Z equal to 0. So if my water, phase 1 is water, phase 2 is air. So we get this. And we basically get P1 minus P2 plus 2 H gamma is equal to 0. H is equal to 0 because it's a flat interface. And so P1 is equal to P2 at Z equal to 0. And this is the air one. So we know this is P naught. And remember that this is my P at Z equal to 0. And pressure I already know is minus rho GZ. So this is equal to C. So this means C is equal to P naught. Right, so we discussed this under this point. Any questions on this point of C is equal to P naught? Any confusion? Yes.
Where does P naught come from?
So that's the second phase. So remember that this is the pressure in the air phase, right? This is air. So the pressure in the air phase is given to us P is equal to P naught everywhere. So it's the air phase pressure which we have to equate. Okay. All right. All right, so we get this. So third part, which is generally solution, is very simple in this case. We just know P is equal to, we can just substitute and get P is equal to P naught minus rho GZ. So this is my pressure. All right. Any questions at this point, under this point? So we basically started the Navier-Stokes equation. We removed all the velocity terms. We get grad P is equal to rho G. And then we integrated and got the answer for pressure with a constant, and we applied the fluid-fluid interface boundary condition, got the constant and got the pressure formula. Okay. Now the fourth step, which we did not have last time, we will do this quite commonly now, is force, calculating force. Okay. And I want to really emphasize this portion in this class, and this will be a little bit more advanced than what you have done previously. Okay. So we will start to be very systematic in the way we calculate force. And I also want you to kind of really appreciate that everything is self-consistent here. We cannot have any, inconsistency when we calculate these forces. So this is the water phase. And we have pressure. So pressure, now I'll just write it. Remember, pressure is P naught minus rho Gz x, y, z. Pressure is equal to P naught here. Okay. So this is my system. And now let's say, hopefully I can get the colors to match. So this is, let's say this is A, phase A. This is phase B, the bottom one. And this is phase C. Let's say green here. Phase C and D. Okay. So let's take a darker green. C and D, and I'm not doing E and F, but those are the back and front faces. Okay, so you have 6 faces, and what we want to really find is F pressure, or F, let's say F, yeah, let's say F pressure is equal to FA plus FB plus FC plus FD plus FE plus FF. Okay. So those are 6 faces, and I want to basically integrate on all the faces. Okay, so we want to integrate on all the faces. Okay, any questions at this point? So we want to calculate force. Yes.
Why is the force a vector on each? So why is FA like?
Because force has to have a direction and the magnitude, right? So force itself is a vector. So yeah, and it can mean any direction on any of the faces. We don't know yet. Right, so force, so that's why every phase will have a vector. It could be, we don't know the direction yet. Okay. Any other questions? So summation, you want to sum over all the surfaces. This way, if it was not a square block, by the way, like you have in your homework, it's a hemisphere or a sphere submerged, then I will only have one surface. If it's a cylinder, I will have two, one circular, two on the sides. And I have given this homework problem in earlier years. Like a block like this, right? Something like this. So we have this is a top like this. So something like a trapezoidal block. So you also have 6 faces, but you can have a 5-face surface or whatever. So you want to sum over all the surfaces. That's the point. Okay. So whenever we think of force, what should we think of? Stress vector. Okay. So please, this is really important. Whenever you think of force, please just remember stress vector. Okay, so now F of C, let's focus on the C vector. F vector of C, I will have stress vector ds. Okay, so there are some choices here. Okay, some choices here. First, could someone tell me that what should be the end direction? Because this is a C phase. What should be my direction, normal direction, and why? Sorry, go ahead. And so Tim says EX. So why not minus EX? Could be either, or should be one of them. So it should, yeah. So it is EX because it should always go into the fluid. So remember, first thing, we are trying to find the force on the block, right? We're trying to find the pressure force on the block. So this is force on the block. And on the block is equal to by the fluid, right? So it is equal to by the fluid. So my n vector now should point into the fluid because that's a definition. Okay, so my n vector is in this case Ex. Okay. Now, what is my stress vector? Stress vector is defined as n dot sigma. Okay, so n dot sigma. N dot sigma ds. Okay. Let me just again specify. Maybe if somebody was confused. into the fluid. All right. So what should be my sigma? Anyone? Mean stress tensor. So I can't make progress until I know my stress tensor. So good. So what is sigma's definition? Minus pi plus tau, right? So don't forget, basically my point is there is nothing new here, but sometimes the way students get used to doing this is just kind of like sort of skipping some of these steps, but I want you to really see all the steps, because then it's just about being systematic. This is not some, you just want to be really systematic. There is no trick here. You just want to really just systematically go through it. Okay. Sigma is minus pi plus tau, and tau is 0 because velocity is 0, right? Velocity is 0. So when we have flow, now this tau, as you will see, tau will start to become finite, because I will have, if I have a velocity gradient, then I will have some shear stress. Okay. Right now there is no velocity, it's hydrostatic. So this becomes n dot minus pi ds, right? And this is simply minus p and ds, because n dot I is simply n. So if you dot the n with identity matrix, it just becomes n. Okay. Now, could someone tell me anything interesting to see here? So any kind of, and this is maybe a little bit of a vague question, but what I'm looking for is what is a correct characteristic of this pressure force, looking at the sign of this equation. What do you think? And this is a result that has stayed with me for a very long time. So this is a negative n. Okay. So the pressure force acts opposite of the direction of n, and n points into the fluid. So minus n will point away from the fluid. Okay. So it's very common to remember that pressure always pushes. Okay, so I've never forgotten this line. A hydrostatic pressure always pushes. It can only have a push force. It cannot have a pulling force. It has to have a pushing force. Okay. So let's say if you are inside water, remember the water pushes you up, right? It will always push you. It can never pull you. A pressure force, by definition, will always end up pushing, having a pushing force, because it always points into the solid, into the interface of your. Okay. So it's trying to always push you. So it's minus n. So that's the direction is very important. So remember that this is pointing because of the negative. Force points into the solid in this case. Okay. Yes, yes. Yes. All right. So before I simplify further, what do you think my ds should be? How do I calculate ds? What is my interfacial surface area? Perfect, right? It's perpendicular to x, right? It's perpendicular to x. So, by the way, I forgot to bring the book, but there is a table in appendix. I always write this in homework, but I forgot the equation number. So in appendix, it actually gives you these differential areas. And if somebody can look it up in the appendix, there is a section which talks about all this. So ds of x is dy dz. And you don't have to remember any of this. You can just look it up in the book. There is a full section on this. And this is the direction of normal. Okay, direction of normal. So my answer essentially becomes minus p and dy dz. Okay. And I will get to you the appendix number 2. So this is how you do it. And what are the limits of dy dz? Anyone? So geometrically, yes, please. Yeah, so almost there. So remember, it's at the center line, so minus a by 2 to a by 2. So remember that we are basically, we use kind of origin at the center generally. So minus a by 2 to a by 2, a by 2 to a by 2. Okay. So generally that.
So we also found
So great question. I was just about to ask a clicker question on that. So just a second on that. So yeah. So this is basically your integration. And remember, we have already calculated pressure. Okay. So calculated pressure. And let's ask what Sophie was asking just now. So what do you think would be the pressure force here? Let's take a quick poll here. What is the correct formula for pressure force on the right face? Okay, which is the C face. So let's give another maybe 30 seconds more, and then please to get your answers in. Okay. So I just write down. All right, so let's give, okay, I think everybody has almost responded. So let's see. Okay, so there's some sort of split, which is not unexpected. So what is correct is actually C. So most of you did get it right. So first thing is it should be negative EX. Okay, and remember that we are integrating over this entire surface. Okay, so we're integrating over this entire surface here. So half of it is, which is Sophie's question, half of it is submerged inside water. So here pressure is P naught minus rho g z, and here pressure is P naught. And so that's why, remember, half of it is above water. Okay. So you will essentially get, and the pressure is not a function of y. So y can just simply come out of the integral because pressure is only a function of z. So it becomes minus a times, and there is an ex because that's the direction of n plus ex. So it's P naught dz. I think I'm sorry. Yeah, P naught dz 0 to a by 2 plus P naught minus rho gz dz minus a by 2 to 0. I believe that should be hopefully the correct expression. Let me just check. Yes, okay. So that's the expression you get. All right. So any questions on this? This is very important. So what is the pressure force in the right face? You can calculate. Okay. It has two parts, one from the air, one from the water. And you can just integrate this to get on the C face. Now, what do you think will change if I want to calculate the pressure on the D face? The D face, what should change in my equation? Any other ideas? Yes, any thoughts? So Julia mentioned the direction will change. Would my pressure change on if I'm thinking about D and A? So D and C faces, does the pressure change? Why not? Any thoughts? So pressure is only a function of height. So if I'm moving from this phase to this phase, like it doesn't matter. I'm just displacing in the x and y direction, right? Z direction has an identical Z dependence on on the C phase and the D phase. The only thing that changes is the normal direction would now be in the minus EX direction, right? So as you can imagine, basically this side of the face is being pushed here, this side of the face is being pushed here. The two forces are identically cancelled out, right? That's because of symmetry. So I hope you can see this. So basically FC plus FD goes to 0. Similarly, the back and front faces will also go to 0 by adding them. But A and D will not go to 0 because one of the faces is in the is in the top face, which is like, on the top surface, and then the bottom surface, which is in water. Okay. So the only two faces which remain are FA and F. Okay. Any question on this? Any question here? Anything that's confusing? Oh yes, yes, definitely. Yes. So this was just illustrate how it works, but you don't have to. And in a normal problem, no problem. You can just argue about anything. You don't have to worry about it. But I just wanted to go through the process of showing how the process works out if you have like an interface sitting half inside water, half above water, and so on. So it was just literally do for illustrative purposes. You don't have to do it at all. Yes. Sure. Yeah. So that is basically what is happening is I skipped a step. So here basically, remember this is a function of z, right? Then I have ex dy dz, right? So I can take this integral separate because dy is it's not nothing else is a function of y. So I can say this is minus a by 2 to a by 2 minus a by 2 to a by 2. So I can say pz ex dz times dy. When you integrate this becomes a. Make sense? Any other questions? All right. Okay. So let's basically now all we know is F pressure. F pressure is FA plus FB. And so FA is the top surface. So this will become, and I'm not doing the full, but I hope you can see it will come out to be minus P and ds. And this will also come out to be minus P and ds. Okay, so let me just quickly sketch this out here as well. A face is this one, B face is the bottom one. Okay. So what's my normal direction for A face? This is XYZ. What is the normal direction for A face? Right? Plus E, right? So this was a question that a student asked me. I had never appreciated it. They said, well, I want to find the normal direction pointing into the direction of water. But remember that this block is actually in air. So the fluid is now the air fluid. We cannot say the stop fluid. The stop fluid is only point, is the only interface is air solid, right? So we cannot think of water anymore. So here we have to only point towards air. Okay, so it'll be plus EX plus EZ. And what's the pressure? What's the pressure? P naught. So P naught. So it's minus P naught minus P naught EZ. And what's the ds? So it's a z phase. So ds is dx dy. Okay. This is the A part, and A phase is the B phase. So now what's, yes, please. Oh, so you can go from, so so the integration limits are not arbitrary, it's set by the definition of the definition. So you always want to use, so you may get the right answer you need to use in this case, but I would just remember what the coordinate system is. Because the coordinate system is set at the origin, I would just say always use the same, use like the coordinate system. So you get what your coordinate number is. Any questions here? Anything that's confusing? All right. So what's my pressure in the, what's my normal in the B phase here? Minus EZ, right? It's minus EZ because it's pointing here. It's pointing into the water phase. So it is minus EZ. And this is very important. What's my pressure? So I want to, somebody has to tell me what's the pressure. How can I find the pressure at the bottom of this? So good, good. So I am hearing some whispers which are correct answers. So P naught minus rho g z. Remember that this is at z equal to minus a by 2. Okay, yes, please. No, so basically your pressure function will also change now. So yeah, so good question. So what Noah and Sophie are asking is, what if I change my coordinate system? Okay, I don't follow this idea that origin is in the middle. I want to change my coordinate system. I want to say my x, y, z start from here. Okay, you are being adamant that no, I want to use this coordinate system. You can use that, but then in that case, remember that your boundary condition will no longer say at z equal to 0, pressure is P naught. It will say at z equal to a by 2, pressure is P naught. So your definition of pressure will change. So you can choose any coordinate point, you can be outside the block, anything, it has to work out at the end. So this is true because we chose the coordinate system in that. Okay. So that's what this is. I would say yes. That's generally, I would say, generally finding something in the reference frame of the solid block in the center is the easiest. Like in your homework, you have a sphere, so just easiest to start the origin in the center. So I would say yes in general, but sometimes you may have scenarios where, let's say the block is submerged within the water phase, so you may want to have an interface. So coordinate system will be generally, I would say, it's not necessarily one way to do it. It's more of a practice thing that you get used to finding the right coordinate system. In most cases, we will just give you the coordinate system. You won't be asked to kind of find yourself. But it can be sometimes confusing. All right, so we go here, and so essentially this again here, remember that this P naught is not a function of x and y, and this is also not a function of x and y. So what you simply get is minus P naught a square easy, and here the minus and minus cancel out, it becomes plus P naught plus rho g a by 2, because z is minus a by 2, dx dy is a square easy. This becomes minus P naught a square easy plus P naught a square easy plus rho g a cube by 2 easy. Okay, so this cancels out, and you get rho g a cube by 2 easy, which is actually equal to minus rho v submerged g vector. Any questions here? This is a good exercise to just make sure you are understanding everything there. Everything is clear, there's no confusion. Any questions? Yes, G vector, sorry. This is G vector. So I've written a vector just to show you it's like opposite of gravity. So remember gravity is minus GGZ. So I've written it, that's what is the minus sign at the end. Any questions here? Anything that's confusing? Not clear? All good? Yes, please. Oh, yeah. So that's because of the minus EZ. If I understood your question, there's a minus and a minus here. So that's why it becomes a plus.
Below that, though, so the one that minus.
Also, it's minus rho g z, and z is minus a by 2. So remember my pressure is P is equal to P naught minus rho g z. So P is equal to at minus a by 2 becomes P naught minus rho g of minus a by 2. So P naught plus rho g a by 2. Right? Oh, that's because of the gravity then. Sorry, maybe Just want to, okay, wait, let's, this is because I want to write gravity as minus G easy. Just for that, just to show you that the direction of the net force is opposite of that of gravity. That's all. So, I mean, don't get confused, but this is kind of redundant information here. Just trying to show it's in the direction opposite of gravity. Gravity is in minus easy, it's in plus easy. Yes. That's a scalar. So that's a scalar. So remember, we say G vector is equal to minus G easy. That's just because that's how you typically write, gravity is 9.8 meters square per second. So meter per second square. So that's why typically it's written like this. Any other questions? Yes, please.
Would you also, like, as another method of approaching this, kind of be able to do all of it at once and just use divergence theorem?
Yes. So that's essentially what you're asking is the derivation of Archimedes principle. So instead of actually trying to do minus P and grad P and ds, you can convert it into a volumetric integral using divergence theorem. And if you do that, you will essentially get it in the answer. Right? So, but I think as a practice, we're kind of doing it. But yes, that is actually the derivation of Archimedes principle on an arbitrary shape. The book has that, but we don't follow it in practice. So you can use divergence theorem. In your homework problem, obviously the intention is to calculate pressure force because that's the kind of habit of doing this. But yes, at the end of the answer has to match because of the size of the element. Any other questions? All right, just to kind of just to tell you what the supplementary video does is supplementary video goes through this problem that there is like a rod like a cylindrical block that's presented in like this. This is your supplementary video. So you will do this, and your homework is essentially this. Okay, so your homework is this. So in the supplementary video, I talk about the cylindrical coordinate system, and in their homework problem, you will do the spherical coordinate system. You'll have practice of all three coordinate systems. With the same problem, same idea, just that remember now, when I'm thinking about pressure here, my z coordinate is changing, right? So pressure on the longer surface is no longer constant. It's actually changing. So you integrate out. There are some steps, and again, please do follow the video to kind of will help you kind of understand how to approach this. I just want to kind of show that it's very similar to what we're doing in class, just a little bit more. No, right? The buoyancy force is still there. It's just a balancing with gravity.
Oh, okay.
Yeah, so it will still be there, but it just balances with gravity. So what Sophie is asking is what will happen if I have a block like this, then you will still have pressure here, still have pressure here. And it's just that it will come out to be rho g a cube easy because full block is submerged. Right now I'm getting only a cube by 2 because half of it is submerged. So that's just that's what you can expect. And that makes sense, right? Because when it's fully submerged, my pressure will not be minus rho gz at a by 2, it will be rho gz at minus a, kind of like that. So that way you can always find that it will work out to be just rho g a cube by it has to follow because of that. Okay. Any other questions? You can choose anywhere. So you can say I want to choose here. You can choose z equal to 0 here. Whatever you wish. It just has to be consistently used to get the right pressure. So if you use it as same z, then you will get P naught minus rho g z. But let's say if you say, oh well, I want to use here, you will not get P naught minus rho g z because at some z value the pressure is P naught. Sorry, yes. Sure, yeah.
So the pressure is like the pressure force is the same on the whole block.
No, right? That's the difference.
We don't have to see the
Oh, so that's not so. So we are finding the total pressure force. So good question. So I think what you're getting confused is, so we are finding the sum at the end. So pressure force is different at A, different at B, different at C, different at D, different at E, different at F. C and D cancel out. E and F cancel out, and A and B do not cancel out. but that's a net pressure force. But there is a pressure force which is different. So let's say in an exam I say calculate the pressure force on face C. Don't use Archimedes principle. Actually, that's you just want to have you calculate the pressure force. So you just find pressure force on that face. And or imagine if I actually this was a exam problem I had once made. I stick a block on a surface, right? Something like this, right? In that case, I'm kind of attaching a block on the surface. So then there will be a pressure force here, right? And there is no fluid on the other side. So there will be a normal force from the solid wall on the block. So that's going into rigid body force balance that you might have done in your courses. There's a normal force now the solid block will apply. There's a normal force, it's stuck. So if I stick a block here, the board will apply that force, right? And then the water is applying from this side. So the normal and that force are balancing. So yeah, it's just a balance. So yes, the pressure force is different on each surface. The net force, pressure force, is the Archimedes force or the buoyancy. Any other questions? All right, so it's 12:51. Let's start at 12:55, and then we'll start unidirectional flows. Yeah, basically, can you show rather than doing all of this? Yeah. If you have system, it's Archimedes or it's but I prefer to do it like this. You can have force
I guess I know the show is just
Yeah.
Right, that is the right thing.
If you spend but you will not have this exam. You want to show that. So the good thing is when you kind of indicate all that comes out, it just works out really well. So it's good to kind of see. There are some steps when you go through it. So you know the answer, it's just that you kind of follow the steps.
So when you have a block section, right, it's like steady under. You have to be able to like calculate.
So if the surface, you know the surface, there is no distance.
But as you go further,
It doesn't matter. But the pressure on both surfaces will be high. Good question. So a block like this, a block like this, the net pressure force cannot change. Because the submerged volume, Archimedes principle that the submerged volume is the same, right? If you want to think about pressure forces, though, so let's say this minus V is P plus K, right? So P equal to P naught minus is much lower. Minus rho G is this force plus rho G minus, right? And this one, and P naught plus rho G plus K. Right? But now I say this is some H plus I. The difference of pressure will always be this. It gets cancelled out.
there is a difference in pressure.
There's a difference in pressure. There's a difference in pressure at each phase, but the net cancels out. So it doesn't matter. So there is no height, there is no stable height or unstable height.
The raw amount of pressure on that object is going to increase.
So there is nothing to just pressure. It's always the force. So just remember that. The net force is the same. So you're right. Absolutely, the pressure is increasing here. The net force.
Thousand feet, it's like
Because this will only happen when the against the same. solid block of water. Otherwise it's not a stable configuration. So the question is, if it's a stable configuration, then the densities have to match.
So if this is moving like right now in real time, then that would apply.
Yeah, that doesn't apply anymore. So what you're asking, if the densities are different, if the densities are different, then anyway all of this is moot, because then I have to find next node equal to M create mass acceleration. That's why you get this equation. So you have to yes. You have a question taken a moment.
This might like we can't figure it Okay, okay. Because I thought it was, because we have our RS.
No, that's the thing. So what is your direction? So not easy. Why is that? So that so you make it the right answer and have to the direction is
So it will be this.
because the X and Y that you might have to cancel out. And that's because you remember that we are changing the direction. You can never get that very power.
That's what I asked you last time. Because I get reading like just focus on like that.
So you never focus, you don't have to make this. You basically, and I will mention in the summary that break down the
Okay, so. Okay, so, well, except this here. Because the answer, I mean, actually, it makes some sort of sense. Like, I mean, sort of makes sense.
That's why, because you're not open down here application like
Oh, this is still. Yeah.
Yeah, sounds good. All right, so let's begin. We have to get to the next problem. So just as a reminder for your, and this is also mentioned in the homework, please look at the appendix 8.7, 24, 25, 26. There is a lot of nice information in the appendix, and I have never memorized these formulas, so you don't feel at all that you have to remember anything about geometrical change. You can just look it up in the book. Okay, so you may have to go from ER to EX, EY, and EZ for your homework. And we also do this in the supplementary video. Okay, so I will show you in the supplementary video about this, and this will also help you in the homework problem. So remember that you can look up these relationships in the appendix. All right, so let's now move to chapter 7. This is important for your homework. Homework 3, problem 4. And we are now going into unidirectional flows. All right, so what we have discussed, stress tensor, stress vector, what is the force, we have discussed Hydrostatics equation, and then we have done a hydrostatic problem. Then we have learned how to calculate forces by integrating a stress vector systematically through all the surfaces. Okay, so now we are saying, well, we will go to unidirectional flow where one component of velocity is non-zero. So you have always three components of velocity: Vx, Vy, Vz. So hopefully will remind you of the 1D steady problems we used to do, right? So only one component is changing. Okay, only one component is changing. In the next week, when we go from here, we'll discuss nearly unidirectional flow. So kind of like approximately 1D steady problems. So next week we'll make it a little bit more complicated and say there are two components of velocity, but only one of them is dominant. Okay, so that's next week. But today we'll focus on one component of velocity when it's non-zero. That's unidirectional flow. And
In general, some of you know, well, why do I care about unidirectional flows? Like, do I ever get them in real life? And I don't know how many of you use a rheometer or it's an instrument to measure viscosity. I would say for soft materials, if anybody of you is interested in soft materials, rheometer is the gold standard to understand the fluidic properties in a system, and that actually still uses today state of the art. Rheometer will use the solutions of one dimension because it just rotates in one direction. Or it has an oscillating direction, but still one direction. So just remember that unidirectional flows, even if they may not happen that often in real life, you can design instruments around them. They're very instructive. Microfluidics, the very first part of microfluidics, like maybe 2010, was almost primarily one directional, one unidirectional. Now it has become more complicated, more better microfluidic designs and so on. But unidirectional flows are very practical. They are actually used, even though you may not see them in the so don't just to kind of mention that. So we will start directly with an example because I think that's the best way to learn this unidirectional flow. So think of, and this is a problem many of you may have done before. So think of parallel plates. These are solid plates. I'm not so think of these are like solid plates here. All right, and the coordinate system is x, y, and z direction. Okay, x, y, and z direction, and I'm flowing some fluid through this, such that pressure is P1 here, pressure is P2 here, and this distance is L, and this distance is 2h. This is so it's like two plates. So this is two plates, parallel plates, and I have a pressure difference. Okay? So initially, remember in the first part we had a hydrostatic problem. There was no velocity. Now saying we have two plates, and we are just applying a pressure difference to make the fluid flow through the channel. Okay, so it's a channel flow, sometimes called channel flow. So ignore z dependence. So just remember, we will ignore z dependence. We will assume the system is steady, fully developed. We will discuss a lot more about this in part 3, but for the purposes of this part of the course, just remember that gradients and the x direction are assumed to be, for velocity to be 0, x direction. Okay, so velocity is 0, and ignore z dependence at all, and ignore vz is equal to 0. So we also assume that the velocity in the z direction is 0. All right. So this is kind of like some of the assumptions we are thinking, and ignore gravity. Ignore gravity. So ignore z dependence, velocity z is equal to 0, fully developed, ignore gravity. All right. So right now I have yes, okay, question. Yeah, just before and just after this step, yes. And you can think of this height, so this distance and width of the plate W, and but we are not really thinking about the z direction right now. Okay? All right. So what we really want to find is, remember now I have 4 variables. Now I have 3 variables: Vx, Vy, and P. Okay? So pressure, velocity of x, velocity of y, and pressure. Okay? Vx can depend on x and y. Vy can depend on x and y, and P can depend on x and y, right? Because and they cannot depend on time because it's steady. Okay? These are my variables. All right. Any questions just for the problem setup before I start going with the governing equations? All right. So number 1, first step, governing equation. I just want to write them in full form so that you can see. Del V x by del x plus del Vy by del y is equal to 0. Rho Vx del Vx by del x plus Vy del Vx by del y
And you can always look up it in the book. Don't have to memorize any of this. Hopefully all the terms are correct, but if you find typo, don't hesitate to let me know. So this is the full form of equation I have. Left hand side, then I have a pressure gradient, and then I have in general, as you can imagine, currently I have written the equation assuming there are two variables, right? Vx, Vy, and P. So two directions in velocity, three variables in total, and two velocity directions. But we have said that this flow is unidirectional. And sometimes students don't like when I have done this like before, just directly jumped into assuming that Vy is 0, but I want to show you how Vy is 0. So remember that del Vx by del x is equal to 0. This is an assumption because a fully developed flow. And we'll talk about this in part 3. But if this is true, what happens to my continuity equation? What happens to the first term? Anyone? 0, right? If del Vx by del x is 0, then the first term is 0 because that's del Vx by del x. So that implies del Vy by del y is equal to 0. And that implies that Vy is equal to constant. Does everybody agree with this? That Vy is equal to constant, right? You disagree with this? It could be a function, right? That's a good point. So it could be a function of x. So that's a very good point that so what Saurabh is saying, that it is constant, but it could be a function of x right now. So how will I find this? Any thoughts? How I want to make progress and I want to simplify the system, but and do I have to just use this and carry on, or I can kind of be clever and make some thoughtful suggestions? Any idea of what we can employ here? I heard the right answer. So remember that this is a liquid solid interface, so there is no penetration, right? We will have velocity in the y direction. Velocity in the y direction at y equal to plus minus h to be 0, right? No penetration, right? And that has to be true for all x values, by the way. So that's why that you will essentially you can argue that this is equal to 0. Okay? So because of no penetration, I cannot have any velocity in the y direction. I cannot have any velocity in the y direction because it's constant, and it cannot even be a function of x because no penetration applies at all x's. Right? So it applies at all. Vy is equal to 0. Yes. Yes. So it's 0 at y. By the way, yes, just remember that this is equal to y equal to plus h, and this is y equal to minus h. That's why we used a 2h. 2h. Okay, so the normal velocity, remember normal to the plate is y. So that's why y component Vn, right? Vn is equal to 0, no penetration. So Vy is equal to 0. So because of that, you can drop this out. So remember that it's actually, this doesn't matter, my Vy is simply equal to 0. Okay, I hope you can convince yourself that Vy is equal to 0 because of continuity equation and no penetration condition. And my Vx is not dependent on x because of fully developed condition given to us. So Vx is only a function of y. Any questions on this? Vx is only a function of y and Vy is equal to 0? Yes. Because you have been given that it's fully developed, so it doesn't depend on x. So del Vx by del x is equal to 0, so it means it's constant in x, so it's only a function of y. Make sense? Any other questions? All right. So with these assumptions, let's try to simplify our governing equation. All right. So I want everybody to kind of participate here, and because we want to cross out terms. So first term, Vx. So this term, Vx del Vx by del x. What is this term? 0, because del Vx by del x is 0. Okay. Second term, is it 0? Why? Because Vy is 0. Okay. And it's important to go through this exercise because as you will see next week, we'll start to think about scales. The terms may not be exactly 0, they may be small. Okay. So that's why I want to kind of make sure you kind of get in the habit of why these terms are 0. Okay. The first term fully developed, second term Vy is 0. Third term is 0, just del P by del X. We don't know. We currently don't know. Okay. Then del square Vx by del X square is this 0? Right? Because it's a derivative of del Vx by del X. When del Vx by del X is 0, if I take another derivative, it doesn't matter. This is simply equal to 0. So I have just these two terms remaining, which are non-zero. Okay. So just these two terms remain, which are non-zero. All right. Now, second part, second equation. What happens to the first term? Vx del Vy by del X? 0 because Vy is 0. Okay, this is 0. Then this term also 0 because Vy is 0. Should del P by del Y be 0? We don't know yet. We don't know yet. Okay, so we don't know yet. And then again, there is Vy and Vy here. This goes out. The only term that remains here is this and these two. All right. So I get this. I get minus del P by del X is equal to mu del square, plus mu del square Vx by del Y square. And I hope you will allow me this liberty to write this as d square Vx by dy square because Vx is only a function of y. So I have gone from del to d, and I have said minus del P by del Y is equal to 0. So these are my governing equations. Any questions on these governing equations? The two governing equations from the two directions I have in the system. Any questions, sir? All right. So remember that Vx is only a function of y, and right now my P is a function of x and y. Okay. What does this tell me? Del P by del Y being 0 tells me that P is not a function of y. So P is not a function of y. So P is not a function of y, and I can just forget this term. This is P is not a function of y. It is only a function of x. So I don't have to use that term. What I'm only left with is minus dp by dx, because P is only a function of x, plus mu d square Vx by dy square. Yeah, because del P by del Y is 0. So it's constant in y. It doesn't depend on y. Right? Del P by del Y is 0. It doesn't depend on y. It only depends on x. Yes. Oh, in this problem, we're ignoring gravity. So yeah, I must have mentioned it, but in this problem, we're ignoring gravity. Yeah, so ignore gravity, but you can have a system where there is flow plus gravity. So, but we are ignoring gravity for the time. Yeah, that's a good question. So sometimes the point is very different. So what I'm saying is when we are talking about unidirectional flow, why did we have to use flow penetration? The idea to show that is, remember, it's sometimes confusing because there are two directions. So there is x and y, but the component of the velocity is only v. So sometimes you get confused. So it's also, it should be consistent. Like that's the whole point. That no, it's not like you're violating. So it's a more rigorous way to come to the same point as the direction. But I would say for more practical purposes, you will not have to show that you just tell you it's only Vx will not do anything. So I just wanted to show it, that's all. Any other questions? All right, so we have this equation, and let's now focus on the boundary condition. Boundary conditions. So this is a liquid solid interface. So what are my boundary conditions in liquid solid interface? No slip and no penetration, right? So Vn, and this is a stationary solid, that these are plates. So Vt is equal to 0 and Vn is equal to 0. We have already used this. Already used. So I'll focus on this Vx is equal to 0. This is the parallel direction. And Vx is equal to 0 when at the interface. And the interface are when y equal to plus minus h. Y equal to plus minus h. All right, third step. Solve.
So how can I solve the above equation when I have both pressure and velocity? Any thoughts? But how can I integrate with respect to y when there is both x and y? I have a dp by dx. I have a so I'm giving the right answer. Any I also have thoughts. What's going on here? So I have a dp by dx and I have a d square dx by dy square. How can I integrate both? I mean, I still have a derivative of both in x and y. So how can I integrate it? Right?
So so this is basically the idea, and which is what I also suggested. Remember, this is only a function of x, and this is only a function of y. If I have a function of x plus a function of y to be 0, they can only be 0 when both of them are constants. Okay? It has to be the case. Otherwise, I cannot generally write a function of x plus a function of y to be 0 unless both of them are constant and equal, right? So that's why we can just say this is equal to constant. And remember, I know the pressure at x is equal to 0 is P1. Pressure at x is equal to L is P2. So you can even write this as minus of P2 minus P1 by L. So you can even write this is constant, right? Pressure is constant. So it's linear essentially.
Del P by del x is
let me just explain this one. So minus del P by del x is constant. And what I'm saying is it will be P2 minus P1 by L minus, because it's just simply the subtraction by the length. Okay. Or if it's constant, you can integrate this and apply the boundary conditions for pressure. I just so if somebody is confused, you can say, well, this is equal to C. Then you will get P is equal to Cx plus minus Cx plus B. And then you can use the value for P at x is equal to 0 to be P1, P at x is equal to L to be P2. And then you can substitute this back to check that C comes out to be minus P21. Okay.
so that's just more formally somebody just always check.
So any questions, Ken?
Yeah, so that's what I'm saying, that if it's constant, you can basically integrate and get a linear profile. In a linear profile, you can apply the boundary conditions, but you can also take the linear profile, which is constant. You just simply subtract the two values. That's what I do. That's why I'm
Makes sense? That's also what you can do, or you can just show it to be fully. So minus delta P by L. Okay, so what we are saying is mu del square Vx by del y square minus delta P by L is equal to 0. And this is constant. This value is constant, right? P2 minus P1 by L. And when you integrate this twice, and unfortunately I don't have time to show this, so that's why I just want to show this to you. Integrate this twice, you will get Vx to be an apply boundary condition. What you will get is you will get out to be minus delta P by L h square by 2 mu into 1 minus y by h whole square. Okay, so this is what you will get out to be your final result. Please do try this yourself, and you will be doing a very similar problem in your homework.
but slightly more complicated than the current than we did in class. It's kind of just an extension almost of this. But the idea being that here you can expect that the velocity profile is parabolic, no slip at the surface. So this is y direction, this is x direction, and so this is essentially a parabolic velocity profile. Parabolic velocity, yes. Sure.
So we have. We don't have.
You don't have to solve it. Yes, that's a good point. Yeah. So what Sophie is saying is, can I just not solve for it and keep it minus dt by dx here? Absolutely, you can do that. You can also do that, but I was just trying to show it in terms of d minus d by L, but delta t by L is dt by dx. So you just simply use that dt by dx. It's constant. It's a constant number. So you don't have to solve it. Okay? But just remember that in this linear directional flow, dt by dx is constant. Okay. Just remember that. This will become important when we talk. Okay, so I will briefly discuss this next time, and I will end now because I know we are running out of time. Is that now that we have the parabolic velocity profile, after this, we essentially want to calculate average velocity, which we will do next time, average velocity, and we will talk about force balance. And for force balance, we have uploaded the supplementary video, which talks about this, and this is what you do in your homework as well, doing a force balance on this. So once you solve, then you calculate the stress vector. Once you have the stress vector, you integrate the forces, and then you will see how all of these force balances each other out, because they have to balance it. So that is what we do in your homework, and there's a supplementary video on the same problem. But I'll also talk about this briefly in the next section. Okay? I just want to mention this in case somebody wants to do the homework, over the weekend or something like that. So you can still do it. So all the homework 4 problems we have covered the material except the force balance, which we will do next time.